Next, we'll find the pH of a 0.010 molar nitrous acid solution. So let's begin by writing the dissociation equation for this acid. HNO2 plus water yields H3O plus NO2 minus. So let's write our ICE table. That stands for initial, change, and equilibrium. We're going to put a double line between our products and reactants. We're going to put a single line between each of the reactants or products. We don't care about the water because it is a liquid and its concentration isn't changing in this case. So plugging in our initial value for the acid, 0.010, so essentially we have no hydronium initially and no anion. So we're losing X of the acid, gaining X of the hydronium, and gaining X of the nitrite anion. At equilibrium we have 0.010 minus X, X, and X. So we're going to set that equal to the K for the acid. The Ka is equal to H3O plus times NO2 minus over HNO2 at equilibrium. So plugging in the equilibrium values, we're going to have X squared over 0.010 minus X. So let's go ahead and plug that in. So that's equal to X squared over 0.010 minus X, and we're going to set that equal to the Ka for this acid, which is 4.6 times 10 to minus 4. If we assume X is small here, then we get 4.6 times 10 to minus 4 equals X squared over 0.010, and X would then be equal to the square root of 0.010 times 4.6 times 10 to minus 4, and that would be equal to 2.1448 times 10 to minus 3. If we check our X is small approximation, we put on the top the thing that we subtracted. That's our X divided by the thing we subtracted it from. So that would be our X divided by the thing we subtracted it from. 0.010 times 100, and that gives us 5%. So our approximation is invalid. So we need to go back and work this problem using the quadratic formula. So we go back to the point at which we assumed X is small, and we don't make that assumption, and we go ahead and get this in the quadratic form. So the easier way to do this is to go ahead and so we back up to the point at which we assumed X is small, and not making that assumption, we need to figure out how to get this into the form of a quadratic equation so we can plug it into the quadratic formula. And this can be a little bit tricky, so I'm going to pull some mathematical manipulation here. I'm going to take my whole denominator and multiply both sides by it and say 0.010 minus X, and then I'm going to divide. Okay, so go ahead and put that. I'm going to erase this over here. Getting ahead of myself a little bit. Okay, so that cancels. Now I'm going to divide both sides by the 4.6 times 10 to minus 4. Okay. So that will allow me to rewrite my equation like this. That will give me 0.010 minus X equals X squared over 4.6 times 10 to minus 4. And now I can say that this 4.6 times 10 to minus 4 in the denominator is the coefficient of my X squared. So let's rewrite that. 0.010 minus X equals 1 over 4.6 times 10 to minus 4 times x squared. So this is my coefficient of x squared. So now I'm going to rearrange my equation a little bit and bring this x squared term to the left. I have 1 over 4.6 times 10 to the minus 4 times x squared plus x minus 0.010 equals 0. And obviously when I moved that term to the left, I had to change the sign on everything to get it into this form. So now I can plug it into the quadratic formula. X is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. So x is equal to minus 1 plus or minus the square root of 1 squared minus 4 times 1 over 4.6 times 10 to the minus 4 times negative 0.010 divided by 2 times 1 over 4.6 times 10 to the minus 4. Okay, and when I solve for that, for x, that gives me x is equal to minus 1 plus or minus 9.3785 divided by 4348, which gives me x is equal to 0.001927 or negative 0.002387. We can discard the negative value because we can't have negative concentrations. So x is equal to the H3O plus concentration at equilibrium, which is equal to 0.001927. So we can calculate our pH. The pH is equal to the negative log of the H3O plus concentration, which is equal to the negative log of 0.001927, which is equal to 2.72. So the pH of this solution is 2.72.